Alright, so today I'm going to be answering a question that was asked on another video, and the question was transmission of electricity compares sinusoidal AC voltages produced as a result of the uniform rotation of a loop in a constant magnetic field with reference to frequency, period, amplitude, peak-to-peak voltage, and peak-to-peak current. Basically the question is asking, it refers to generators, and it's saying what is the effect on the voltage versus time output of a generator when you change various factors? For example, the rotation speed of the coil, the number of turns in the coil, and that sort of thing. So I'll be attempting to answer that today. It does refer to voltage versus time and current versus time, but I think I'll just focus on the voltage versus time because the current versus time is going to be the same effect ultimately. So the starting point, and you can see I've already written some stuff on this piece of paper. The starting point for us is Faraday's law. So I'll try to get this in the frame here. So Faraday's law tells us that the EMF equals negative N times the change in flux with respect to time, where N is the number of turns in the coil. Now just a reminder that flux is a measure of the perpendicular component of the magnetic field lines that pass through the coil. Okay, so let's have a look at how the flux changes as the coil does one rotation. So I'm going to say, and I've drawn the picture here already, that at 0 degrees, so initially, the coil is going to be in the upright, the vertical position, and at that point we have a maximum number of field lines passing through the coil. You can see that the field lines are completely perpendicular to the coil. Now 90 degrees later, so it's done a quarter of a rotation, so it's gone from here and then it's gone now to the horizontal orientation. We can see that the flux is now going to be 0 because there is no perpendicular component of the field lines with respect to the coil. The field lines are completely parallel to the coil, which means that the flux is going to be 0. Now 90 degrees later, we're back to the vertical orientation. You can see here that we're back to the vertical orientation, but now because the coil has rotated 90 degrees and 90 degrees again, the field lines are going the opposite way through the coil with respect to how the coil was initially oriented. So I've just put a negative sign in front there. So don't get too caught up on the negative sign. It just indicates that the direction is opposite as to what it was initially. It's not the exact same situation that we had at the very beginning. Now 90 degrees later, we get to 270 degrees, and again we're back to the horizontal orientation, and we've got that the flux, I forgot to write that in there, that the flux is 0. Again, and then 90 degrees later, now we're at 360 degrees, we've done a full rotation, we're back to the initial setup, the vertical orientation, and the flux is back to a maximum and is equal to B times A once again. So just looking at it, it's kind of, you see a bit of a pattern where it's basically going from maximum positive to 0 to maximum negative, back to 0, back to maximum positive, and raises the question, is it a cosine graph? Because that's really what the shape of a cosine graph is. So that's something that we'll look into a little bit later on. Now let's look at the effect of changing some of the different factors. So what is the effect of changing? And we'll look at 4 different factors. The first one that we'll look at is the number of turns, which is N. So that's going to be, that'll be the first thing that we'll look at. What is the effect of changing the number of turns N? Well, remember that EMF, as we can see, EMF is given by negative N. And again, don't worry too much about the negative sign. That just indicates that the induced flux will oppose the change in flux, which is what Lenz's law tells us. But the magnitude of the EMF is going to be given by N, which is the number of turns, multiplied by the change in flux with respect to time. So that means if I, let's say, double N, you can see that that's going to end up doubling the EMF. Or if I have N, it's going to have the EMF, and so on. It's a proportional relationship. The second thing that we can look at is the magnetic field strength. magnetic field strength, which is denoted by B. What that would do, if we go back to looking at how the flux varies throughout the rotation, we can see that if I were to, let's say, double B, then that means that the maximum flux would also be doubled. Now, when we have a flux of 0, obviously that's not going to be affected by changing the magnetic field strength, but there's still going to be no perpendicular component to the coil. So what that's going to end up doing, if we were to double B, that means that the change in flux would be doubled, because it's going to go from 0, and now B times A at the maximum, when we get the maximum flux, will be twice as big as it was before, right? So that would serve to double my change in flux with respect to time, so it would double the EMF. Another one that we could change would be the cross-sectional area of the coil, A, and it's the exact same effect as changing B, because we can see that the maximum flux, right, when we're at the vertical position, is B times A. So if I were to, let's say, double the cross-sectional area A, then that would end up doubling the maximum flux. So my change in flux with respect to time is going from 0, and now double that maximum value. The change in flux with respect to time would also be doubled, right? So what all of these would do is that this will affect the amplitude of the EMF versus time graph, but not the period, right? Because our EMF versus time graph, think about it, EMF is synonymous with voltage in this situation, and our EMF versus time graph, when it's alternating current, is just going to be a sine curve, like so. So if I were to change the number of turns, the magnetic field strength, or the cross-sectional area, all that would do is that would increase the amplitude of this sine graph. That's what it would do. Now, this here is the period. So this is the amount of time that it takes to go from the beginning, so this would be like 0, 90-degree rotation, 180-degree rotation, 270-degree rotation, 360-degree rotation. So this is the amount of time it takes to complete a full rotation, right? It's a cyclical graph. So all three of these things would affect the amplitude of the graph, and we'll sort of talk a bit about how it does that later, but they would not affect the period, because the period is going to be the amount of time it takes for the coil to make a full revolution. And changing the number of turns, changing the magnetic field strength, and changing the cross-sectional area is not going to affect how quickly the coil is rotating. So that then brings us to the fourth, which is the rotational speed, which I'll denote as omega, which sort of looks like a W, but it's a Greek letter omega. And the effect of changing omega is that it will affect both the amplitude and the period. So this will affect the amplitude and the period of the EMF versus time graph. All right, so that will affect both the period and the amplitude of the graph. And to understand why that's the case, it should be pretty clear why it would affect the period. Think about it, it's going twice as fast. That means that the time taken to make a revolution is going to be half what it was previously. So it should be clear how it's going to affect the period. It may not be as clear why it's going to affect the amplitude as well. Well, looking at Faraday's law, we can see that EMF equals negative n times change in flux over change in time. And so what you're actually doing is you're changing the change in time. So if you are rotating it twice as fast, that means that delta t is going to be halved. And since it's an inverse relationship between EMF and delta t, that means that if delta t is halved, that EMF is actually going to be doubled. Now, if you had a situation where delta t was doubled, like let's say you're actually rotating it more slowly, twice as slowly in fact, then of course that would then halve your EMF. So what I'm going to do is I'm going to go through a few different examples, and we'll see how changing various factors would actually change the graph. You're going to be expected to sketch various graphs and the effects of the changes. So the first example that we'll go through is, let's say that we triple the number of turns. So I'll draw my EMF versus time graph that we start off with, just a regular sine graph like so. I've drawn it with a dotted line, and now we're going to triple the number of turns, and that's going to triple the amplitude, but it's not going to affect the period of the graph. So I would have to triple this. So let's see, 1, 2, 3. It's going to go sort of off the chart, off the page a little bit, but it would be something like that. So the period remains the same, but the amplitude has been tripled. What if we were to halve the magnetic field strength? Well, that would halve the amplitude of the graph. Now let's look at the situation where we double the rotational speed. So rotational speed is doubled. So that's the original EMF versus time graph, and now we're going to double the rotational speed. So as we know, doubling the rotational speed is going to halve the period, right? So instead of it taking this long to do a full rotation, because it's going twice as fast, it's only going to take this long to do a full rotation, which means that we should get a full sinusoidal cycle in half the time. So you can see it's basically being compressed by a factor of 2. And we also know that that's going to, well, let's go back to Faraday's law here. That means that we're having delta t, inverse relationship, it's going to double the amplitude. So the graph is going to have double the amplitude and half the period. So both things have been affected. So we should get something that looks like this. I'll do my best to draw it. Should be something that looks like there we go, something like that. So we can see that the amplitude of the graph has been doubled. It doubled as best I could. And instead of getting only one cycle in that time period, we've actually now got 2 cycles because it's going twice as fast. Now if we were to do the opposite, and let's say halve the rotational speed, then the opposite would happen. So let's have a look at that situation. So example, rotational speed is halved. So I'll draw the original EMF versus time graph, like before, with a dotted line. There we go. So that's the original EMF versus time graph, and now we're actually halving the rotation speed, so it's going to halve the amplitude, and it's going to make the period twice as long. Again, think about it, it's going twice as slow as it was before, so that means it's going to take twice as long to do a rotation. And I want to talk about the actual nature of these graphs. The flux versus time graph, is it a cosine versus time graph? Why is it a cosine versus time graph? Why is the EMF versus time graph, why is it a sine graph? So let's have a closer look at what's going on as the coil rotates. So I'll draw a bit of a bigger diagram. And there we go. So I've drawn this is my coil that's rotating inside the magnetic field. That's the north pole of the one magnet, south pole of the other magnet. And the coil at this point has rotated, and again we'll say that it started off at the vertical position like before, and we'll say that it has rotated through an angle of theta from the vertical position. Now, if I draw in my flux lines, and I think maybe I'll do this in red, just so we can differentiate the different lines here. There we go. Draw some of these in. So there's my flux lines in red. Now, what I'm going to do is I'm just going to focus on just one of the flux lines. And each one of those lines is a vector, and it can be resolved into different components. So I'm going to just look at just this one here, and we're going to resolve it into two components, one that's perpendicular to the coil and one that is parallel to the coil. Because ultimately, remember the definition of flux, it's the perpendicular component of the field lines. That's the bit that we're interested in. So let's have a look at this one field line here. There we go. Alright, so this is the situation that we have. We're just looking at that one field line. There's my north pole, there's the south pole of this magnet. It's rotated through an angle theta. Just going to have a look at this one field line here, and I'm going to resolve it into, as I said, two components, the parallel and the perpendicular components. And it's very much like inclined planes, if you can remember doing this before with inclined planes. It's the same exact idea, except instead of the gravitational field, this is now a magnetic field. Alright, let's have a look here. So we're going to have our components. Alright, so I've marked off my two components in red. This one here, that's my perpendicular component. And you notice it's perpendicular to the coil. And this is my parallel component, which is parallel to the coil. Now this angle here is theta. That means that this angle here is going to be 90 minus theta, because you know that they're perpendicular. And so if this is 90 minus theta, right there, let's see if I can get that in there, that's 90 minus theta right there, then that means that this angle inside, because these two angles here, because that's the vertical line and that's the horizontal line, that also has to add up to 90 degrees, which means that this angle inside here is theta. Now in terms of the magnitude for the flux, it's given by B times A. So if this is BA here, and notice that we've got a right triangle that's been created there, and that's actually going to be the hypotenuse of that triangle is B times A, and I'm actually interested in the perpendicular component, which is given by, it's going to be given by cosine of this angle, because it's going to be the adjacent side over the hypotenuse, and so the perpendicular component is given by BA times cosine of theta. And remember that theta, it is the angle that's inside this triangle, but it's also the angle between the coil and the initial position, which is the vertical position. Alright? So what that means is that flux equals BA perpendicular, as we know, but as we've just seen, that perpendicular component is given by BA cos theta. So flux equals BA cos theta. Now, because the graphs that we're sketching, it's not flux as a function of theta, it's not EMF as a function of theta, they're actually a function of time. Let's see if we can express theta in terms of time. Well, we're talking about our rotational speed omega, and when we talk about the rotational speed, we're talking about the angle that the coil rotates through every second. So for example, if the coil is rotating at 2 pi radians per second, that means it does 1 revolution every second. So the definition of our rotational speed is the angle that it rotates through per unit time. So there it is there. So our rotational speed, omega, equals the angle that it rotates through divided by how long it takes to rotate through that angle. It's a bit like v, its speed, equals distance over time. Except our distance in this case, because it's not actually moving laterally, it's rotating, so our distance now is actually measured as an angle, not as an actual linear distance. So that can be rearranged to be theta equals omega times t. And we can then substitute that in to now get flux as a function of time. So instead of it being flux equals BA cos theta, we have flux equals BA cos omega t. Now, this is really useful for us because, first of all, it actually confirms what we already knew, which is that our flux versus time graph is going to be a cosine graph, right? Maximum positive to 0, maximum negative back to 0, like what we talked about at the beginning. But it also gives us a way to figure out the equation for our EMF versus time graph. Now, this goes a little bit beyond the VC physics study design, but most people will have a background, if they've taken methods, they'll have a background to understand this part of it as well. We know that Faraday's law tells us that EMF equals negative n times change in flux with respect to time. So delta flux over delta t. But when we're talking about instantaneous changes, we really need to make these changes in flux and these changes in time as small as possible because we're dealing with curves here. We're dealing with cosine curves, for example. So the correct treatment of it, if we're dealing with continuous changes in flux, is that we should write it as EMF equals negative n times d flux dt. So in other words, we can see that EMF equals negative n times the derivative of flux with respect to time. So this allows us to get an equation for EMF as a function of time. All we have to do is take negative n and multiply it by the derivative of flux with respect to time. So there's my equation for flux with respect to time. It's a cosine function. The derivative of a cosine function is negative sine. So it's going to be negative BA sine of omega t. I'll write that down. BA sine omega t. And using the chain rule, we know that we've got to multiply by the derivative of what's inside with respect to time. Well, the derivative of that is just going to be omega. So we'll multiply that by omega. And what we end up getting is we get the negatives cancel. So we get NBA, which is kind of interesting, times omega times sine omega t. And that's our equation. So NBA omega sine omega t, which explains why our EMF versus time graph is always drawn as a sine graph. There's a lot of interesting things that can be seen here. We can see that the amplitude of this sine graph is going to be given by NBA omega. So if I grab one of my EMF versus time graphs from before, you can actually see that if we look at either one of these ones, that the amplitude of the EMF versus time graph is going to be given by NBA omega. So this up here will be given by NBA omega, and this would be given by negative NBA omega. And it also explains even further the effect of omega, of changing omega. Because I can see here that if I double omega, so I rotate it twice as fast, well, that's going to then double the amplitude of the function. But omega is also inside here, so omega is also going to be your horizontal dilation factor. I guess actually it's going to be 1 over omega is your horizontal dilation factor. So if omega is doubled, then that means that the graph is going to be squished by a factor of 2. If omega is halved, it's like replacing x with x over 2, well, that's going to stretch it out by a factor of 2, but it's also going to have the amplitude. So I think it's nice just to go into the mathematics because it sort of helps to further explain why changing omega in particular ways has two effects, right? So we can see because omega appears in the equation here and here, whereas the other three things, N, B, and A, only appear out front, so those things will only affect the amplitude of the graph. They will not affect the period of the graph. So as I said at the beginning of the video, I'm only going to go through the voltage versus time aspect of it because the current versus time would be basically the same. If you're interested in how do we go between the voltage versus time graph and the current versus time graph, you're just going to use Ohm's law. V equals I times R, which means that I equals V divided by R. So what that means is that if we know what the voltage versus time graph looks like, all we've got to do is just divide by R and we'll get our current versus time graph. So that means we can take our EMF versus time equation right here and divide it by the resistance, and now it's going to be a current versus time graph. So obviously that it would have a slightly different amplitude because we're dividing by the resistance, but it's still going to be a sine graph, and the effect of changing omega would be the same. The effect of doubling the angular speed would have the same effect. It would double the amplitude and it would have the period for the current versus time graph as well. So I'll let you fill in that one if you want to. Hopefully that sort of explains things. And if anything is unclear, write in the comments and let me know if you have any questions.